So, okay, like last time, actually, we talked more. We talk about what? We talk about Viola Jones, a detector for face detection, and also like we talk about like eigenface and feature face for face recognition. We'll actually talk a little bit more about like object detection today. Actually, among object detection, face detection is one of the easiest one because more or less like everyone's face like have the same color tone, like more or less the same, and all of them have the eyes is there, like it doesn't kind of move around too much. Roughly speaking, like if you try to recognize, say even pedestrian is much more challenging because like you can have much more different kind of pose, even though like and also color as well. Like everyone like wear different color of shirts and so on. And of course, like, if we're trying to like detect like animals, they have many more different poses, right? So it will look a little bit more about like object detection. Actually, basically all the state of the art approaches, P deep learning basically. And we also like going through a more systematic approach today. So first of all, like this is just kind of repeating what I'm saying. Like for example, if I try to kind of detect a dog here, like there are just simply many different poses for a dog, right? So all of them is a dog, but they all look quite different if you think of that. And also like more challenges that appear like in object detection, like because of viewpoint, cluttering, occlusion, and so on and so forth. And this is like kind of very much a high-level paradigm like for object detection. So first of all, we should specify what kind of model we want to use, and we want to generate some hypothesis. Hypothesis will be like where exactly you believe there will be like objects there. Then you want to put score like on the hypothesis, how likely there's actually object there. Then try to resolve some detection result. Mostly is like, for example, long mass suppression, that kind of like if you have for the same object, if you conclude like okay, there's several boxes kind of like enclosing that object, then you want to like just pick one of them or like merge all these boxes into one box. So let's start with like specifying an object model. So last time when we talked about Viola Jones is like using like simple filters, right? So here the you can think of filters as also like some kind of like statistical not exactly template, but template would be like a pretty much widely used approach. So one of these templates will be like HOG, basically like we appear in the homework and so on. So and of course I to say more kind of precisely, I should say like I transform into a HOG domain and use that like and to construct the template and just do template matching and so on. And Dalal Triggs that we are going to talk about, the algorithm is mostly based on this. And we can have like part model. This articulated part model is a very much refined part model is going into like layer and layers, a hierarchical into pretty down details. For example, like you have a person there, you expect that he has a hand, and the hands he has fingers, and so on and so forth. You try to model each part components of those that object. An intermediate approach would be like you have a hybrid template and part model. So you just that actually basically, for example, the deformable part model we'll talk about later on. And so of course we can go for some 3D-ish approach. This is not exactly very popular now. But it's hard to say. It's also like sometimes like algorithms are not popular because of the constraint we have like at the current moment. Maybe in terms of like capturing the 3D models, and also maybe in terms of computational power. But the idea would be like you just basically, maybe for example here we just capture key points among the object of a 3D model and try to kind of like build the 3D models from the extract the key points and so on, and try to match these 3D models with what you expect the 3D model is supposed to be for a kind of reference object. And this is a kind of like even go further. Like the earlier is like have a key points of the 3D models. There's this one that you have a entire model is like kind of created by deformable 3D model, and then you can do matching and then trying to parameterize that way. So I'm looking at these videos. I just think, do we really need to put so many obese people there? Anyway, so I'm actually if you are interested in approaches like this, there's a kind of free software called Make Human, and you can play with that. Like you can just it's a free software. I only tried that on Linux, but I'm sure like it has a Windows version and so on. So you can parameterize everything, like construct the face. I mean, like tune like different. I mean, basically you can build yourself your own model, like just parameterize all the characteristics of that yourself. But of course, it will be quite I get tedious. And so of course, it sounds like the more complex model will be more appealing. But of course, it's not always the case, because inference will be much harder, and of course, computational complexity, like this requirement will be bigger as well. And after we select the model, then we need to try to generate some hypothesis, right? So the simplest one is that we just do it exhaustively, just scan through the entire image. That would be the sliding window approach, where just assume everywhere is a potential candidate that can be an object there. But of course, if you do sliding windows, you also need to slide across a different scale of the image. You need to say create a pyramid of the image, and then just scan it for each of these level, like different scaling level of the images, and then like each windows we can separately classify. It is more or less what we did like in Viola Jones, right? And another approach would be look for key points first. Let's say if you have some, for example, if you are quite sure what you're detecting. For example, you're detecting a particular book, you have the cover, it's like pretty sure what it's like, then you can just go for, like, for example, look for this descriptor for some key points on the book, and then just look for this corresponding key points like in the image, and then you just match them, right? So in that case, you don't need to scan through the entire image, and relatively speaking, will be more efficient. So this will be like a more general description here. Like you can find the key points, and then like you match the code books. Like if you don't just have one book you're looking for, or like one object that I mentioned that you're looking for, maybe you have several different objects, then you just match with key points of all the objects in what you're interested in. Then you will have like places that you find those key points, right? Then you just, those places will be all the candidates. Then maybe you can go through some statistic voting and so on to just say, okay, here like you have high concentration of key points that have the objects, then it's likely to be there. Then we can pay more attention there. So another one is a region proposal, and it's quite popularly used in recent object recognition, object detection approaches. For example, like if you also look into like approaches like after deep learning, let's say RCNN and so on, they use region proposal. Of course, a later version they create their own region proposal network as well. But the original idea for region proposal would be like basically based on segmentation. Right? You expect like all the objects will be more or less look like have some uniform texture there, right? So if you try to segment like different things out, then basically you can start with like kind of like clustering the pixels together. Actually, we'll talk more about that like next week when we talk a little bit about like segmentation. So basically, you cluster some of these pixels together, then you just cluster more and more, then you have patches, and then those patches can be your region proposals. And there would be like several possible approaches to have candidates, object candidates. And then amongst those candidates, then you can just go the hypothesis, right? Just basically go through whatever object recognition classifier you have, then just trying to see if like you have the object there, if the score is like larger than certain threshold, then maybe you make a box there and so on and so forth. So then you need to resolve some detection problem, like that, as I mentioned, like you have some typically like some maximum suppression issue there, that you may have like one object is here, and then like you have like several candidate boxes that encoding that object. Then you just need to merge these boxes into one box. So it's relatively easy. For example, like you can, if you have two boxes like that, if the overlapping is larger than, let's say, 0.6, 0.7, then you consider them like to be kind of like targeting to the same object. Then you may kind of like just take the average of the coordinates of those corners to create a new box. And also like you can take advantage of some context of reasoning of the scene. For example, like if I'm trying to look for a car, then maybe I can exclude some of these. I expect that the cars cannot find yet, so I can exclude like some of these candidates. For example, here, like here, and so like for example also like pedestrian detection. So we can maybe exclude here, that stuff like that. And actually, this is a quick slide that I just remembered. I just realized that I never mentioned how to evaluate object detection. I just assume that everyone knows that. But this is just for completeness a quick just quick go through of this. So basically, like if you try to do detection, you for example here is trying to detect pedestrian here, say. So you have ground truth like this yellow boxes, say encoding all these ground truths here, right? And let's say this is like your recognition result, that you get the predictions here, here, here. So this one is more or less correct, right? This is kind of this is apparently half. So then how do you evaluate that? Actually, how do you evaluate that? So for this one, like, okay, like we always talk about precision and recall. For you guys haven't fallen asleep yet, like what's just for this particular example, like what's the?
It's a false positive.
Yes. But just for this image, like let's say what's the precision for this image? Like can you give a number? Let's say what's the precision?
Number of true detects, so would be 1, 2, 3.
Yes. It try to the classifier make two feedbacks here, like three different kind of output boxes here, but only one of them is correct. So therefore, the precision is like 1/3. So how about recall?
the bounding boxes or?
Mm,
I forgot the formula, but it gives the ratio of coverage, like how many were there and how many were captured.
yes, yes. Actually, I don't remember that formula, but I just try to think of like what's the reasonable kind of definition of recall. So I guess recall probably means that like if you have so many true stuffs, how many of them you can actually capture those, right? So I have two of these are true. I only catch one of them, then recall probably should be 50%, right?
We captured two pedestrian, right?
Oh no, this is a ground truth. The green boxes are
the
the
green box is the ground.
yes. If like that 2 year, then it will be like 100% recall, like in that other case. So and this you can form like tables or like all these have like other different names like false positive, false negative. I honestly I don't exactly remember all these. Like sometimes I have to go to Wikipedia, like hit misses. But I mean like you know some of this is enough. Like precision recall, I can't always remember precision recall. And with precision recall you can okay, yeah, that's just more example like. You can trade off precision and recall, right? For example, like if I make lots of bats, I would say like from the classifier, just like everywhere, I say like that's a potential objects, then I will increase the recall. I most likely I will catch the one, catch most of the actual objects, right? But then the precision will be very bad. Like it will go, or like the other way around, I can be really what's that word? Careful. I want to look for a more elegant word, but anyway, that the classifier just more or less doesn't say anywhere is an object. Then in that case, like the precision can make it pretty high, but then the recall will go down, right? So that's for like it's always a trade-off, right?
One question.
Yes.
The bounding boxes.
Yeah.
Are there any emphasis on those? Like the bounding boxes for the ground truth and the prediction?
Yes, actually that part is difficult. Typically, what people do is like just say if it's more than 0.5 overlapping, then we'll count it as like they will set a threshold there, like maybe like actually 50% is typical. Sometimes they will specify like I would say 50 or like 70, but 50 is like typical. So more than 50, I would say is correct. So then, as I mentioned, you can have like a precision and recall kind of trade-off here. So I have a PR curve, and that's also like old school, like in statistics, they have this ROC curves as well. It's like put in a slightly different way. And of course, for this, as you can see, like if your system is perfect, then your precision and recall curve should just be a linear line like that way. So if you have a perfect system, perfect classifier, but that's really, really difficult. And typically you have something like that, you can compare approaches, like, okay, this one, for example, like faster RCNN is here, DPM is here, HOG is here, so you can see a precision and recall trade-off. And sometimes it's hard to say like which is good or bad, okay, by the way, like also like I want to mention like FH precision and MAP because this is also like a evaluation metric I use pretty often. So as you see this PR curve way, so if you look at this precision here, the FH precision is just FH over this recall, right? If I have a perfect kind of system, then the FH precision will be just 1, right? Or 100%. So so that's basic FH precision. And so therefore like higher the FH precision is better. What this MAP mean is like mean FH precision and mean over like several classes, because sometimes you have more than one class, right? So each of the class will have a PR curve, then you just FH over all of them, then you have. So as I mentioned earlier, that's like you typically need to specify the percentage of overlapping. So like 50% is typical. So therefore sometimes you see people say MAP at like 0.5 what they mean is like they count like everything overlapping more than 50% is considered as co-ed classification. Yeah. Co-ed detection. Yeah. Co-ed classification, assuming like they need to both detect the object and classify that correctly. Yeah.
One question I've
Yes.
seen sometimes there's multiple bounding boxes
Yeah.
detecting the same object.
Yeah.
That actually increases the precision, while recall it doesn't really help with the recall.
Yes, that will increase the.
Like
You have multiple boxes. Actually, you improve your recall but decrease your precision, because in that case it's basically you just have randomly floating dots, right? I say everywhere say objects. Then I will.
No, it's true detection, but just the bounding box is a little bit slightly different. So it can still have more than 0.5 overlap.
Yeah,
but
yeah.
It's just, some of them are completely submarked, some of them are like.
Yes, but as long as one of those hit that, then you can say that one is correctly classified, right?
So should
that
we
box.
credit 1 point to the precision, or should we actually count all of the bounding boxes as true detection? That will increase the precision.
Precision, okay. Precision will be over all your bets, right, or all your guesses, right, from the classifier. So you can put lots of guesses everywhere. So when you're saying overlapping, for example, I have a bottle here. I have one box that's kind of like correctly captured that. I have another box like all kind of. Oh, okay. What you're saying, like if two of them
My
is.
two positives are increasing. So the precision will look good.
Let's see. Yeah, that's a bit tricky. I don't know people will treat like this because, but I guess
It's not about cheating. It's that like when we do real time.
Yes, but
like inference, these things happen, and I don't know how to calculate the precision. Like
you can still say that. I mean, like it's fine because I'm sure like you have multiple of these, but at the same time you will also.
I need to count as one. Like I don't want to include.
Yeah, if you want to count as one, then you should do the long maximum suppression rate. So, I mean, here, so you should just merge the boxes together. Actually, I think OpenSea have that function. That people like after you get the box there. Actually, I can even show you the code afterward. So there's a library you can just, but even you can do it very easily. Typically, what people do is like overlapping is more than something. Then you just merge these two boxes by just averaging out the coordinates of the corners. So then like this, or you can pick the one. You can have different rules for that, but averaging out can be one possibility. So for example, here maybe this.
How would I know how many boxes I should cluster together to? By how close they are, or the library already does that.
By how close, how much overlapping, I guess you can say. But I didn't dig into that because, again, like the library is there. And for that part, I didn't really dig into that. But
is it Python library or OpenSea?
OpenSea will have that.
Okay.
Yeah, but I don't think this is kind of like state of the art research, so I didn't really pay attention into that. I mean, I shouldn't say it's not state of the art. Like it's probably not people like researching it now for the moment, not people most interested in. So and this is some evaluation. So as I mentioned, we talked about Viola Jones last time. So it's a summary slides of some of these detection techniques here. We are going to talk about Dalal Triggs and also like this what's that? DPM, deformable part model. So first of all, Dalal Triggs actually is it's pretty easy to understand algorithm, like especially you guys already go for HOG. It's basically just computing HOG and then go for a linear SVM to do classifying. So it has a little bit tiny details here, so I will go through that. So basically, he proposed the detector like target for pedestrian when he first drafted the paper. So he explicitly, he just assumed the people have this size, basically 64 by 128. This is all his training data is more or less like that. Then they compute HOG inside this window there, then using SVM, and as I mentioned, have like long maximum subtraction to remove overlapping detection. So a little bit more details here, like he has this word 64 by 28, and then he partition this image patch into like tiny cells, and then like you can try different color space also, like typically you can do grayscale, but also like there's some other color space that appears to be a little bit better. And you can also do grammar conversion, so like you have the intensity of this color space, then you just do some linear adjustment for that. And then afterward you can compute HOG. So of course, like when you compute the histogram, compute the gradient before you compute the histogram, you compute the gradient can be a loss of possibility there. So he picked center, like this car filter like looks like doing pretty well. Then after computing the histogram, the gradient, then you need to just put them into bins. He picked a on side angle like from like 0 to 180, and there will be line bins there, and the histograms have k by k pixel. Let's see, k by k pixel cells. I'm not sure I have case here in anywhere, but anyway, for each of the cell that I showed earlier, that basically each of this cell here, then you compute the histogram, right? Compute the gradient, then compute the histogram. And also like when they do the for the votes there, for the histogram, it's just weighted by magnitude. That's what we did in the homework also. But he adds something like basically have a binary interpolation between the cells. So for example, if you have two cells, like one cell is like at 75 degrees, another cell is 90 degrees. So if your input is at 85 degrees, then you put like 1/4 to this 75, and then a fifth quarter to this 90 degree cells. Bins, I shouldn't say cells. It's kind of confusing. So okay, and then he also did something kind of I would say a little bit ad hoc, and for me it's not quite expected. Like to me, a little bit surprising. So he did a normalization somehow that after you have this histogram for each of these cells, like for example, you consider these particular cells here. So he will kind of normalize the histogram values here across the labeling cells. So the normalization just normalizes into basically 1, something like that. The total, if you consider that histograms are vectors, you want to normalize across, for example, like first normalize across these 4 cells here, the vectors to have unit norm there. And he just put a E here, a small value E here, just to ensure like kind of stability in terms of computation. Then he repeat that like a couple times. And to me, a little bit surprising is like after normalization, then you will have like 4 different outcomes of this guy here. And he basically just cascade these 4 vectors together as output. So it seems like it would be like duplication, right? But because in the sense like you have like 4 vectors and kind of they have scale to each other basically more or less. But he simply cascade them together as the features. So as like here, so you have, so after all this operation, you have what 15 by 7 cells, and then have 9 orientation from the histogram bins there, and then have 4 different normalizations as I mentioned. Then this will be the number of features. And then you use that to go for SVM, and then of course I won't go more detail for SVM. You can just call it from library and so on. So it's just a linear classifying. More or less, you can think of a neural network actually, but like single layer neural networks. Then basically it, right? Then after you train the weight, let's say here is an example. Let's say that's the compute features, and this is the trained weight here, and the bias terms here, and you get the values is positive. Then you say, okay, that's a pedestrian, there's a people there. And that's basically it for like HOG. So in the sense that you're trying to learn these templates that using SVM, where you can think of. And here is just an example, like if you have the image here, you have this HOG future map, like image coming in, like you compute the HOG, then it's like you're going to slide the window compare with this template here after you use SVM to train. Then you have a detection response. Then the high response will be correspond to you have the pedestrian there. Then afterward, like you can just have log maximal suppression. And also, like you're supposed to repeat that for multi-level. You can just create a HOG pyramid to do that. And this is they are from a French group, I believe. Like so, they use the area data set. It was a little bit dated. I won't go through their results now. Let's see. They have this is not exactly very interesting, honestly.
Are these techniques more accurate or efficient?
Oh, definitely not. But it's more efficient.
It's more efficient.
But not accurate. Computation-wise, is compared to like all the methods nowadays. It's still like this kind of old method is. For example, like I can show you I can run it on my PC here without GPU, but you cannot do it on YOLO without GPUs real time, even YOLO. Yeah. So this is like for fun, like to just demonstrate to your parents that you didn't waste the money like studying in college, but I mean, like, I'm tiny project, I guess, maybe, like, or like, if you find a company, they're just trying to get some funding from government for like preliminary stage, just to have something like to get people to take a look, something is working, then maybe this would be something. Because like, for example, in particular, Dalal Triggs is what implemented like in OpenCV, like, can be called like pretty easily, and even in Python. And for deformable part model, I check, and I couldn't find implementations in Python. Like somehow, like in the news group, they say like it only. I tried the C++ version, it's kind of working, but like they don't have the Python version is working. So but as I said, like okay, at least it's better than Viola Jones. Like in terms of like Viola Jones won't be able to detect pedestrian. I believe I never tried that, but I believe so. Like it, yeah. So it cars pedestrian is okay. As here like, it mentioned, like okay, cars and pedestrian is kind of okay, fairly well acceptable. I will show you that, like if you guys don't mind to walk in here. But cats and dogs, I guess, is quite sure it's not good enough. So
what is the fundamental difference in technique between the deep learning and this one? Because I know, like faster RC, and they use SVM to do the predict cost level. But is it at the feature extraction level, like the Hawk feature versus Haussian feature?
You can say so because if you think of, let's see which one you want to compare, like faster RCN. Actually, I would say it's kind of closer to YOLO because if you think of YOLO, then it's more or less still a kind of sliding window approach, even though the windows is kind of like discrete, because you basically partition the image into box, right? Each box you assume that candidates have like different, and also like they have this candidate box there. They assume, okay, you have look at this particular region. I assume that the object can be. Oh, I shouldn't. No one can see me on it. Okay, let me just. Oh, actually, why don't I do that? Oh, can I? So I mean, for YOLO, you essentially I forgot like how many blocks you are going to partition the image, but you will essentially partition the image. Then for each block, you try to look for the object. So it's kind of like similar to like sliding window as well, right? But then you assume that the object have different shapes. Like you will try to look for, okay, maybe this shape, and this shape here, and they call this anchor boxes, and then afterward, everything will be a little ledger, okay? Everything is already trained. So I would say like here, if you compare with HOG, HOG itself, like at least the first, the features itself is not trained, right? Because the HOG is kind of fixed, so you have this template, like the procedure to extract the features is not trained. That's kind of major difference. So what's the question again? I forgot.
So feature extraction is the major difference between, because I know both techniques use SVM or other classifier to make a, like, after the region proposal, use a classifier to say what object was there in that region. So I was just wondering, so the feature extraction is the major difference between the deep learning techniques and the technique you just.
Yeah, I would say feature, because the whole deep learning kind of selling point is basically I train the whole model end to end, right? So therefore, like I no longer kind of handcraft the features anymore.
Right.
Yeah. So if you say why train features is really so much better than handcraft features, then sometimes I think it's a little bit hard to say. Like,
I was thinking maybe deep learning model extract Hawk type features, so that's not the case then.
No, Hawk type features would be quite simple, because it would be just addition. Actually, Viola Jones is very much hard type features in the sense that you just add and subtract. Like you have, for example, like I would just have filters like adding this region and then subtract this region. That would be Viola Jones kind of features. But if you think of like they have a CNN there, like then it's basically, in deep learning you have CNN there. Then your convolutional filter there, like it's a kind of arbitrary filter, right? The major difference is like if you think of all the classical image processing, for all the filters we impose on, typically either it's wavelet or like discrete cosine transform or like Fourier transform, so on. All those filters is kind of have certain, I would say like nice mathematical math properties, but it's not really adjusted to your training data per se. So, but on the other hand, in deep learning, you really try hard to have the filter come match with your data, right? Because you spend so many data there, and then so yeah, then it's not surprising it works so well. But then like at the same time, like it honestly is, just look at that part maybe a little bit high, the whole deep learning area. I'm not sure I mention about that. Like what's the name for that? The professor in Berkeley, the AI professor, is really famous. He has a textbook like modern approach. Should I forgot Stowashow, something like. He I listened to one of his interview with Les Freeman. He said like he mentioned like data is not the new oil, but data is the new slick oil. Yeah. So so I mean like but of course like this gives you results, right? So companies are happy, right? So if you really have data, you just grind it with like really fast computers, you'll get results, right? But in terms of actual understanding, right, we are not better than like decades ago, honestly, for many other of these older approaches. Right? So if you compare with SIF, like I'm sure like Lowe's, like David Lowe, like who created SIF, and so like he has much more insight about like what's going on with the image than people like typically just grinding like but
for deep learning, they're extracting all type of features that are possible, applying all type of filters, and then
yeah, and match with the filters.
Filters or which way.
Yeah, you can think of that way, right? But of course the training part is difficult, right? But and yeah, training part is really difficult. I'm especially GANs actually, when you pay with GANs. I don't know how far you are. GAN is notoriously difficult to train. What people did typically, I didn't really pay too much about that myself, but I watched several of these interviews and like talks. People just say like typically what people in company did is like, okay, they want like 100 different kind of like same jobs for the same thing, like with different seats there, and then the one give you good result, and that's the one, and then I just use the one, and then I publish the paper, and then I can forget the 99 of that. And even like Goodfellow, like the creator of GANs, he mentioned that he has spent more than half of the time just to try to stabilize GANs. And yeah, so but okay. Anyway, maybe.
I think it's harder to make any dipole stabilized.
By nature, it's difficult. Another one I highly recommend is like you guys can listen to or like watch the interview of Yusha Banjo by Les Freeman. Yeah. He just believes that like even though nowadays like companies have all these like exponentially more computational resources than academia, he thinks that in academics still can work on something meaningful. So
there's a line of research understanding what deep learning models are actually learning.
Yeah, there are a lot. Yeah, there are a lot like kind of visualization along that lines. For example, like besides that, maybe one thing he mentioned in the interview is that like the host asked him like what does he think like more important, the architecture or lack of data? What's the more challenging aspect of like trying to make deep learning models work well? He just said neither. And yeah, he believes that like yeah, I guess it's similar to Hinton also like bad pop probably is not the end game. Something is quite certain is that like human doesn't use bad pop way, animal doesn't use bad pop. like in our brain is quite sure that there shouldn't be backpop there, like somehow, but I don't know. You guys are younger. You can switch field like to neuroscience. Maybe just try to collaborate with them like somehow to see like if they can give you more insight like how. Um, but yeah, but I mean like in terms of like new training paradigm. Of course, optimization is really important as well. Like after atoms, more or less people just use atom, right? But is that's the end game? Most likely is not, right? So all these are actually more meaningful research area than just padding the model to be bigger and like maybe you have a model I put another head and then I just classify something else. Uh, that give you a quick, dirty conference paper in some minor conferences, but if you are serious in doing research, then like looking in training methods and also like kind of optimization techniques probably is more uh, worth spending time. So anyway, like I digress so much. Let's see. Oh, okay. I guess I as I promised, I'll just show you some codes here. So as I mentioned, like for HOG it would be pretty easy, right? Here, I have I downloaded this one, the XML file, but you can find it also as I mentioned to Sylvia here, right? Like you have this non-maximum suppression is a you can call it, just pull it out from the image utilities in Python. Oh, it's not from OpenCV, actually from image utilities. So, and then like you don't need to worry about non-maximum suppression. The code is just kind of one line, right? You have this HOG detects the Dalal Triggs here. And if I want that, like you can go like, okay, my capture here, I lower the resolution somehow. Like I just go for like, actually maybe a little bit too low. It's like 320 and 320 and 240. So I can try the, but you see that because I lower the resolution, is actually the frame rate is pretty high. It's almost 40 frames per second. So, but let's see. Can anyone want to try to be a pedestrian as well? So it's kind of okay. Maybe like my resolution is too low. Let me try to make it high. See if it helps. I remember last year I also did this demo also, but I remember it detected me a little bit better. I'm less human this year, and maybe just another computer. I'm not sure. So I increased to like it's slowed down quite a lot. Like I increased to like 4, but it looks like it's a little bit more stable now. I increased to 640 and 480. So like it's okay.
So why would higher FPS it wouldn't detect?
Oh no. You mean no?
You increase the resolution.
I increased the resolution. Okay. I mean like I at the beginning I set the webcam to only capture a resolution like 320 and 240. So resolution is a bit low, but at that resolution is like, because you remember the box they have is, I forgot, is 120 and 64 is okay for one. So it's like the resolution is actually pretty low in fact. But as I said, like, I have no GPUs here. So and if you have a YOLO, even YOLO 3, probably you cannot run it real time with the GPU. And this is the trick. And maybe I quickly also go through the rest. Is like, so I like to just quickly go for deformable part model. It's very simple. Like we mentioned, like bag of part, bag of words, bag of features last time. Actually, bag of words is for NLP, but sometimes it's called this bag of features. And deformable part models is more or less the same idea, but in back of features, you don't actually consider the orientation or like the relative locations of all the parts there. But in deformable part models, I just expect like the eye should be like on top of the nose, not on top, like above the nose, and mouth is below the nose, and so on. And the simplest model will be like this. You have a whole, so you have different nodes that correspond to different parts here. So you have a wood node here that's basically correspond to the entire face in this case. And then you can have like different kind of nodes trying to detect different parts there. And then like it'll be like this, right? So this is exactly same thing, like this example for people here trying to detect. So the wood node will be, if the wood node will be essentially the same filter as HOG. You can use the HOG filters for the wood node, and then you're trying to train to detect like different parts like the head. Honestly, I don't know how they can train like parts like the the arms, and it just looks so different like for everyone. I don't know, but somehow they just train this way. And then like then you have like this global filters, as I said, they call it filters here. Global filter will be for the entire body and entire person, and then you have part filters for different parts. And that's another example, like you have a bicycle model, like you can see like it will need different models like for different view of the same object, right? If you have the frontal view here, it will be very different from the side views here. And also like this illustrate one of the disadvantages of this kind of model. You just need to hand code like every kind of object. So you have object like that, at least you need to determine, okay, which are supposed to be the parts, more or less. And then from there, like you can train that. There's more example here. So then again, of course, you need to go multi-scale, like have a pyramid, that kind of like Gaussian pyramid to capture like objects in different scales. And so I will go a little bit more details now, a little bit. So the model will be more precisely will be like that. So I have let's see. This is the wood filter to detect the entire object, and then I P1 to Pn different parts filter, and B is the bias terms like to basically to adjust like the score like above what you consider is like a detected object. And then VI is the anchor points. It's basically what you expect like your path supposed to be relative to the global object. So for example, if I'm detecting the head here, I expect the white eyes should be here, not too far away, stuff like that. And then DI would be like the deformable cost. So if you have your eyes is like off by 1 cm, like how much extra cost supposed to be. So then the entire cost model will be like this, right? So you have this for let's see, this will detection score like for each of the parts, more or less, and then like this will be the deformable cost for when you have each of the parts is carved away from your desired location. So the deformable cost here will take both the displacement and also the square displacement as input. So of course you can think of this part as kind of redundant, right? But it takes all four of them as input. I guess in the sense you can make this a linear model. Actually, I didn't dig into that, like whether it's a linear model or not, but yeah, I assume it is. So then this will be, yeah, basically repeating what I'm saying. So just break down the overall pipelines here. So if you have and let's say image coming in, Then you have like all these path model. Then you scan through the entire image, right? So you have this global wood filter that have the template that you train to detect the entire person. Then you have these different parts, like let's say the head parts to have another filter, path filters, and other parts here. Then this is an example here. Then you merge the score there. For example, you have different parts. And then the parts also and also you merge with this wood filter. Okay. So let's see. Oh, okay. I have the wood filter score here. It's basically just saying, okay, it's basically the output from the HOG, right? In the sense that if I only consider the entire person, like as a whole, like the brighter spot here is correspond to, okay, that's likely there's a person there. Then each of the parts will have contribution like, to how likely I have the person there, right? Because like, if I have the person is like here, and then I detect a head is here, then there's a better chance that I have the person is here, right? Something like that. And then I need to include the deformable score, and then you also put in the deformable score and so on. Or you can think of these two together, like from this map, and then you put all them together. So then you have the final score for the detection of the person. This is just more example. Yeah, actually. I guess I'll just skip this. I don't know whether I should skip it or maybe not. Let's take a look together whether it say anything meaningful. I copied these slides from one of these. Apparently, like I forgot like where I copied from now. So of course, some of these comments may be dated now because but some of them may be relevant. Like this one, like, as I mentioned earlier, right? So when you change to another category, you include a new class there. You just need to rebuild from scratch, right, for all the parts there. And nice part like about this kind of approach is like once you detach stuff, like each part have meanings, right? So actually, but if you think of that, like if you my other class, like if you look at like post out CNN, like mass out CNN, like with also detect the post, like also like you can get things like similar to this. But of course, like relatively speaking, like that one will be even more it will be quite a bit more computationally intensive because this one I can run it 2 frames per second without GPUs. That one will be like 2 frames per second with GPUs. So can be like maybe 100 times computationally more intensive. And of course, like this kind of model, like you can just merge with any other detection approach. Like potentially, like you can also mix with like deep learning approaches, but even though may not be the best way to do it, because I mean, in the sense like for deep learning, you're already training end to end. What I'm saying here, like maybe you can have earlier layers, then you interpret like what you have earlier, and then like try to mix with approaches like this to yeah, it depends. I maybe I shouldn't comment on this. So anyway, I guess I shouldn't bore you about more on this. And so we can, there's some enhancement of this approach. Like for example, instead of like a star model, have a wood and like connecting to all the parts there. We can also have fully connected models. But of course, like, it would be more computational intensive. So okay, let me just show you the demo there. So it's let's see if I can. Oh, by the way, who use Visual Studio? Do you? I just found that like that's Visual Studio code. I never know that. Like it was because I think it's like since last year they have that. Like I mean it's pretty nice. I'm not a big fan of Microsoft, but that part is pretty nice. It's yes, but only for Windows, right? I mean now they're for Linux and for Mac and yeah, I tried that out. It looks at least the feedback that people love it, so I probably will kind of look more into that. But let's see, yeah, here. Yeah, as I mentioned, like this one I cannot find a Python version. I have a CPP version here. I'm kind of really rusted with my C++. But it's not too bad because I'm just using OpenCV for that. So let's see if I can find the. Oh, actually, I didn't specify the model here. I input the model as a from the argument of the. But other than that, like it's like HOG, like more or less, like the Python version is relatively simple actually. And let me just run that. Actually, I can recompile one this. Oh, okay. This is a reasonably fast because again I'm using like what I have this. It looks like it's a bit more stable than previously, right? Because here is like the resolution is lower. It's my first version. I showed earlier. This is like 320 by 240. But you see that like earlier we have like almost 30 frames per second, right? This is only 10 frames per second, so like 3 times slower than like HOGL. Oh, okay. Sorry, like I don't have connection here. Oh, okay. Sorry. Okay, come back. Yeah. So yes, and yeah, it's kind of so. So even like say 320 by 240 is kind of okay. Maybe I can, like the other one, just set up double the resolution here. It's probably really slow. Now it's like, as I said, it's like 2 frames per second, but it's without GPUs. So therefore, like compared to YOLO and of course YOLO can be like real time when you have a GPU, but this is about the speed of mass RCNN and RCNN, faster RCNN. Yeah. So and that's about it. That's what we talk about today, right? This Dalal Triggs and deformable path model. It was, as I said, like it was the state of the art just pre-deep learning, like 2008 or something. I guess it was still state of the art until like 2012, until like they have that came out. And that's it. I guess we'll probably talk about some tracking and segmentation next week. So I'll see you guys next week.